Well, hello everyone. Good morning, good afternoon, good evening, depending on whichever part of the world you're watching me from. Let me quickly go across platforms and check if you're live. If you can hear me, feel free to comment. Would love to know that you are there. It's always fascinating to see community members who have been attending our sessions for a while now. So it's always very warming to see familiar faces. Okay, I'm checking across platforms. We certainly don't want anyone to get missed out. Okay. I believe most of you would know about AI Planet already, but in every session we see that there are a few more people who are new to the community. So I'll be more than happy to introduce AI Planet, what we do, and then we'll dive right into the session also, because that's what we are here for. So to give a brief introduction about AI Planet, we are a global data science community with the vision to educate and build AI for everyone. And the goal is to solve some of the meaningful problems out there with the help of the community that we have built. So today we represent over 300,000 plus AI enthusiasts from 150 plus countries. And on our platform, you can find a ton of resources like courses, boot camps. There are a set of 7 boot camps starting on today, and live sessions that keep on happening on the platform, which are created by the community for the community. And when I'm talking about that, these Saturday live sessions are one such opportunity where we are fortunate enough to have been collaborating with change makers who are willing to come forward and teach live for you to learn from them directly. So today we have one such guest who is he's a senior machine learning engineer at Siemens. Prior to this, he has worked with some amazing organizations such as QPI, Bosch, Cargill, and at Siemens, he's currently leading. He's a technical lead for automotive parts anomaly detection platform, and he also leads the deployment for the drone intelligence platform developed by Siemens, which is pretty fascinating. He comes from a mathematics background from IIT Roorkee, and he's truly an enthusiast of AI. If you look at his LinkedIn posts, so if you are somebody who wants to learn from him continuously, you can, if you're watching us on LinkedIn, you can anyway find him as a speaker, reach out to him and follow him for staying updated. Now, talking about the session today, we are talking about accelerating object detection with the help of faster RCNNs. So we will explore more about this in the session. We'll also see how it works in action. If you have any queries, you can put them in the comment section. We'll be curating them continuously. And yeah, let's dive right into it. And let me quickly loop in Bijon. Yeah. Hey, hi, Bijon.
Hey, hi, Madit. Good
Thanks.
evening. How are you doing?
I'm good. I'm good. How are you?
Yeah, doing good. Hello, everyone.
Yeah. So the comments at times they could be a bit loud here, but I'm
Sure,
sure they can hear us. But yeah, well, thanks a lot for being on the live session. Very glad to
sure,
have you. Um,
sure,
I'll probably leave this stage to you for you to take the community to the session right away, and then we can start learning.
sure. Hey, hello, everyone. So today, basically, we are going to explore about Faster RCNN. RCNN, Fast RCNN. Basically, it's a RCNN family. Here, it is basically predominantly a topic that is belonging to computer vision and deep learning. So I hope that I will be able to add extra layer of information to what you already have. And yeah, let's dive in. So I will just share my screen and then we'll get started. Just give me a moment. Yep. So is everybody able to see my screen? Mudit, can you just give me a thumbs up that the
Yeah,
screen is visible?
visible, yeah.
Okay, sure. So let's start with computer vision first. You know that what it means, and means how it evolved, and why do we need computer vision as such to make AI more usable. Okay. So, Mudit, currently I am on slide number 2. On the screen, I am looking that it is showing object detection how it started. So, can you please help me sync the slides?
Yes. Once again. Yeah, I think is this correct now?
No,
We're looking at
it is
computer
still.
vision. Uh,
You are looking at computer vision, right, where classification, semantic segmentation, then the other things are written. Is it correct?
Yeah.
Okay, sure.
You're
Thank you.
looking at the screen right now, not the slides that you've uploaded. Yeah.
Okay.
Yeah. So we're looking at,
So
yeah,
I'm just
classification and
confirming once
communication.
again. I am at slide number 3. Is it reflecting on the screen?
The one with medicines, boxes, FMCG,
Yes.
agro and all. Yeah.
Yes.
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 Okay.
Okay. Yeah, let's get started. So, computer vision, what is computer vision and why do we need it? First, let's try to understand it. So earlier, it was simple, plain and simple image processing. It was like that. So what image processing does is, let us say you look at a image in a mobile or in a paper or something, but how does a computer interpret it? For computer, it is collection of matrices, and when you look at a black and white image, usually we treat it as a single channel. Single channel, it means there's just one matrix, and if it is a colorful image, we will treat it as a three channel. Generally, if we talk about RGB format, I mean, you would have already heard about it, like RGB a lot of times, being in engineering. So like RGB has three channels, that red, green and blue, and we already know that the combination of these three colors can help us generate almost all the colors that is possible to be seen in digitally using image processing or computer vision or any for that sake any image based loader. So in image processing we learn about what are the kind of operations we perform on the image, very typical mathematical operations and transforms. For example, contrast enhancement, brightness enhancement. I mean, in our daily life we capture images, right? And then if the images is darker in color, or it is not good looking, we try to increase the brightness, we try to enhance the contrast. Or maybe you have heard about saturation, that we try to increase the saturation to make the image look more colorful. So those are some of the basic operations that we perform on images. But the thing is, let us say you have to teach computer to treat image in a certain way or derive some information out of it. And some of the guys would already be linking it with AI, right? That is what AI is all about. I mean, you have the data, you are able to extract some information out of it and create a knowledge base on which you can take certain actions to make your life more better, or to take certain decisions. That is AI all about. So computer vision helps us there, that given an image, it has some sets of algorithms using which you can extract information out of images, given the set of data you have, and perform certain actions on top of it. In computer vision, usually when we talk about computer vision, and in now today's days of deep learning, there are certain classes of problems that we tackle about, some of which is image classification, semantic segmentation, object detection, instant segmentation. So let's discuss in detail about that what these are some of the tasks. So classification is, for example, if you have an image, it is a very simple task. Suppose it is an image and you want to know whether a certain object is present there or not. It could be cat, it could be dog, it could be car. It could be as complex as a cancer, tumorous cancer in any scan, cancer in lungs. It could be, presence of red blood cells in the slide scan that you have captured through a microscope camera. So that those kind of cases comes under image classification. Now there is object detection. So object detection is, one thing is that you are able to say that some particular object is present in the image, but you really don't know that where it is present. So this will help you localize the object, that okay, if a dog or cat is present in the image, where is the dog, okay, or where is the cat. So this is object detection all about. It is one step from classification, that it helps you localize the objects. Now let's come to segmentation. uh, Segmentation, as the name suggests, you might be already trying to relate with it, that we are trying to assign a particular class to a particular pixel. Okay, so in classification, we assigned a class to a particular image, that this image belongs to cat, And let us say if this is not object detection, we can say, and if you just remove the cat from here, we could say that this image belongs to dog. But here we are classifying the whole collection of matrices. For example, let us say it is 500 cross 512 image. Each and every pixel you are classifying that this is a cat image. But what if I go one step deeper? I want to classify it on pixel level, that which pixel is belonging to cat, or which pixel is belonging to sky, or which pixel is belonging to, let's say, this mountain or vegetation. So here we are doing pixel level classification, that this is a cat pixel, this is a ground pixel, sky pixel, and mountain pixel, etc. Now, as we have evolved, I mean, you could say, yeah, this is great. I mean, we are able to do it, uh, but will it help? I mean, in daily world, we don't have just single cat in the image, right? We could have multiple cats, we could have multiple dogs, as you could see in the image. In that case, there could be certain problems. For example, if you take the case of image blurring, okay, so in portrait mode, we capture images, and what if it is just able to blur the background across only one face? I mean, it used to do it some years before, and you would have seen already, right, that how inconvenient it was that only single person can be captured in portrait mode. So we need to define or distinguish the boundaries of multiple persons in the phone camera itself, right? So that is one of the real world examples. So for that kind of use cases, we need something called instance segmentation. We don't have to just segment the subjects from the background, but we have to also distinguish between the subjects. So this is what instance segmentation is all about. And in short, if we try to summarize this slide, that what computer vision basically is. So computer vision is a field of artificial intelligence that enables computers and systems to derive meaningful information from digital images, videos, and other visual inputs. Although there is a little limitation to this definition, but since this is a very, very introductory lecture, so we have kept the scope to this, because let us say if you deal with signals or something, it is possible to convert them into digital images and then do processing on them. So in a way, not just visual outputs, but even any signal based output can be used to perform computer vision tasks on them. So was a very brief introduction about computer vision, image processing, and what are the problems that we tackle in computer vision. Moving to my next slide, so which is the subject of interest for today. So I mean, there are different kind of problems in industry. I mean, obviously, we have this competitions, and we have open source publicly available data sets. But some of the problems that I selected for this particular lecture, so that people in industry, or maybe even in academia, can connect with the application of actual computer vision in action, that how does industry uses it. Okay, so this problem is belonging to pharma industry, or let's say healthcare. There are instances when, due to the raw material shortage or due to some machine failures, pills get missed while doing the packaging. So, and obviously, if you go to a shop, you purchase a pill of 10 and you find a missing pill, how bad it would be for the company. So this is one of the use case that where we are trying to find the missing pill in the medicine packets. Here, if you see, I mean, usually if you go to very large supermarkets, you won't see, especially in, let's say, US or Canada, where they don't have a lot of manpower to monitor each and everything real time. So a lot of companies are nowadays using automation, using computer vision to get the real time analytics of the objects that are present in the store. So not just this is one of the use case where some of the let's say they have configured that when more than three of this cookies get sold out, information should be triggered, or a notification should be triggered, using which they can add some more packets here. And not just this, I mean, let us say if they get a real time feedback that a lot of people has started buying a particular product, so then instead of, they can order things in advance, that this things we need very soon, maybe using means combining computer vision with forecasting, that these projects are going to finish. So this is one of the use case. Now in large farms, either which are like kilometers long, or half a kilometers long, or 1 kilometer long farms. You cannot, deploy people, because that becomes very costly to check the health of the means produce, agriculture produce, that which part of the farm has ripened. So there you can use computer vision to give you, you will just fly a drone, and drone will give you feedback in real time, that this part of the farm has already ripened, you can start taking out crops from this particular region. And it would be also reducing the human error, and also supplementing them. So instead of taking the surveillance of whole farm, a human can come and look at this particular area only, and they can confirm whether a particular area has the crops have risen or not. I mean ripen or not. So yeah, there are some other use cases as well. I won't go in detail, but this is like rust detection in real time for very very high construction buildings, where it is very difficult to see it from ground. You can just fly a drone and check the health of the whole infrastructure. And this is like warehouse monitoring, where you're monitoring for each and every object, that where they are kept, and getting a real time feed. Now let's come starts with the basic of object detection. That what is object detection actually? So in object detection, first, as we discussed, that you will first see whether an object is even present in the image or not. I mean, let us say I am sitting here to detect a face, or let's say recognize a face. You have to first make sure that a Bijon is present here or not. After Bijon is there, where is Bijon's face, right? So these are the predominantly two stages. The how object detection started. One is classification, whether yes or no, whether a particular object of interest is present in the image or not. And the second stage is localization, that if it is present, then where it is present. And obviously we can go a level deeper, where we can ask that how many of the objects are present. And there could be a case where occlusion is there, that two objects front and all are present. So these are some of the things we'll discuss later, but predominantly you can classify it into, I mean, define it into two steps of classification and localization. Yep, now let's discuss it more formally, that how a computer interprets it, how computer deal with data, how computer gives you output. So object detection, we can define it to locate the presence of objects with a bounding box and the types or classes of the located objects in an image. So obviously, when you're looking at this particular example, you will see that a box has been used by computer to tell you that I know object is present and this is the location and this is the class of the object. But don't think that only a rectangular box is needed. I mean, you can have a polygon box. And when we say polygon, it could be a quadrilateral, it could be trapezium, and it could be like pentagon, hexagon. There's a number of possibilities that you can even do a regression on boundary wise. For example, if you have seen faces, so faces would have, different kind of polygons drawn to localize. So what is the input to the computer? So how does we ask computer to tell us where object is present or not? We send it as an image, which can contain one or none or more than one, obviously none, one or more objects, and output has to be, if there is a bounding box present, you have to give a list, and it should contain labels and bounding boxes, obviously. And when I am talking about this particular format has been defined by us, in the sense we use it, that label box, our dictionary is there and the list of dictionaries there. But there are possibilities of multiple formatting. I mean, there could be Pascal VOC formatting, Coco formatting, and number of formattings are possible. I mean, paddle formatting, different kind of formattings are there. So you give computer this input image, and computer run it through object detector, and it gives you back that this is the label, this is the bounding box, and this is, for example, and using any software. I mean, for plotting, for example, Matplotlib, Seaborn, or OpenCV, we can convert those bounding boxes into a visually appealing bounding boxes and add a text to it, that is cat and dog. So this is one way of whole computer vision, how it works, how computer interprets and give you back a feedback, that where object is present. Yep. So we talked about, that how computer object detection works, how computer treats, and how it gives you a feedback. Now let's discuss, that how object detection started, what were done in the initial years of object detection. So if you are looking at my screen, earlier days, in the earlier days of object detection, how it started was that you will get an object of interest, and then obviously an image will be there, and you have to locate that where that object is present. To do that, a very intuitive idea that would be coming to your mind could be that take this image and slide it over this big image, and wherever it matches, I can localize, for example, this particular place it was, that here my object of interest is present. And this is a very intuitive method, which was uh, at the start was used in digital image watermarking. I mean, in digital image watermarking, basically, if you have to share your images with somebody, you don't want to just share, the original high quality image and expect that they would not use it somewhere else. To figure that out, that your image is circulating, you will just embed a watermark into the image, and to recover it, we used to do this sliding window template matching approach. So, but the problem with this approach is, let us say this car is your region of interest. You were able to detect this car here. But what about this particular car? What about this car or this car? They will get missed, right? And if you want to find them, then you have to again crop them and you have to pass them as an input. But the problem that will come is, what if this car took a right turn or it is coming from front? Again, the computer will miss because it won't know that it is the same blue car which has been given as an input. So there was n number of problems associated with this particular method. So to counter this, people have developed CNN based methods. And when I say CNN, it is basically a convolutional neural network. So convolutional neural network gives you a lot of flexibility and liberty, for example, if your object is changing a little bit, it is translating, it is going forward, it is moving backward. So it is translation invariant. If your object is rotating and you are not able to recognize it with the template matching, then CNN brings in the rotation invariance as well. And it also brings in the size invariance. For example, today this object is this big. What if tomorrow a person captures this particular car from a distance and this looks something like this? Still CNN would be able to counter that. So I'm not going into the depth of the CNN, that what are the each and every property. I will just try to show it to you through an image. For example, this is how a basic convolution operation looks like. That you will have a filter, which you can also call as a convolution filter, something this yellow box. This yellow box moves through image one by one, and it has to cover the entire image. And on doing so, we get a new output, something like this. First of all, don't think that always the size of the image is going to reduce. No, it's not. If the way this convolution filter is walking, it is taking a one by one box at a time. So that we call at stride. And let us say if you want the size of the image to remain same, so what you will think, what idea will come to your mind? It would be that start the convolution filter from here, so that corresponding to this we get an output, this an output, and similarly we get output for each and every pixel. Then the size of image will not reduce. So that was in very basic about that how convolution is done and how convolution looks like. Okay, so let's start with RCNN family. Around in 2014, if I'm not wrong, there was a very good discovery that how we can use CNN um, to perform object detection instead of doing the template matching based approach. And it is basically a two shot detection approach, where in first stage we use CNN to extract region proposals. Let's talk about region proposals here. Currently I'm on screen, the same car screen. So here if you see, that car is just present on this particular part of the image. But the problem is we are sliding the window across image, that how the whole image is looking like, right? We are doing this, and this scans across this region. These are meaningless, right? Why do you want to scan this empty region when car is just present here? So we can extract some features out of the images, and with help of which we should know that don't look in this empty spaces, there are no cars, just look here and you would be able to find some cars. So that is what uh, the researchers tried to solve. They tried to use CNN to extract region proposals out of the image, and doing some classification on those region proposal will tell you the potential region where a car is present. So that is stage one, that use CNN to extract region proposal. In the second stage, a second CNN would be used to classify and further refine the localized of the object. For example, if you get that okay, these are the regions where objects are present, and if these are the regions, then out of which region object is present and what object is that. So that is to summarize that how a two-stage object detection, two-shot detection looks like. And RCNN, fast RCNN, and faster RCNN predominantly follow that particular methodology. Now let's try to break down, that how RCNN works, so that we can understand that how faster RCNN made that revolutionary change and almost bought, almost in a lot of cases right now, object detection to real time. And obviously, if you are thinking that when template matching was run, object how what was the speed of object detection, it was very slow, like 2 to 3 minutes you will take even on Nvidia GPU, which was available at that particular time, to get an output. And obviously, there is nothing to parallelize there, so it was running in CPU only. So 2 3 minutes, 5 minutes, sometimes at that time, even i3 processor I think just came into picture, so it was very very slow. So how RCNN shortens this time? Let's discuss about it. So it scans the input image. I mean, when we are talking about scans, it is extracting features out of the images by scanning them. And by how it is scanning, it is using a convolution filter to slide through the windows and extract features. So that is what the scanning term means here. And it uses something called selective search, which helps it generate 2000 proposals. Selective search in itself is a big algorithm. I will just try to give a brief about it, that what it means. If you look at my screen currently, there was an input image, and there we tried to perform some initial image segmentation. We did some more iteration, and after which we got some result. And the result that you are looking at towards the rightmost of the screen is basically has segmented the images into different possible regions where some object can be present. Right now, there is no intelligence here. It is just trying to find the regions where some potential objects are present, not knowing that which object or where it is present. Okay, so that is what is selective search, and we use it to generate 2000 region proposal. And we get 2000 region proposal. After that, we run CNN on top of all the region proposals whatever we have got through the selective search. Okay, and obviously after running through all the regions, we will get number of features into total number of region proposals. Okay, now we take the output of each CNN and then feed it into a SVM, or you can take it in any classifier. You can feed it into any classifier, but for RCNN, SVM was defined to classify the region, and then obviously use a linear regression to tighten the bounding box. You know that where bounding box is present. So let us say after doing the selective search, you got 10,000 proposals, and you chose the feature output size to be 20 or 30. So you will forward pass all the region proposal, get a feature vector of size 20 or 40, and then you will pass that to SVM to classify the region where it is, whether it is a object of interest or not. And after you get, not after, I mean on parallel, also this will happen. You will run the features through a linear regression also, which will give you a bounding box, probable bounding box coordinate, that where this object is present. So you can see this object is, I mean, you would have already started noticing a lot of redundancies here. For example, this is the input image. You will get, let's say, 1 2 3 4 5 6 7 region proposals. Now this, using this region proposal, you will pass it through this particular CNN, which could be, at that time it was AlexNet or VGGNet, and you will get, let us say, a feature of output 20 or 30 for every region proposals. I mean, first of all, n number of region proposal, n number of region proposal passed through this CNN, and you get an output of, let's say, 20 or 30 for each of them region proposals. And then you pass it through SVM. So SVM will see whether an object is present or not, and then it will try to tighten the bounding boxes. That what tightening means is you will try to be more accurate as possible. When anchor boxes come, I will again revisit this picture and explain you that how exactly tightening works. So that is how you will get a very rough location of your image based on the input image that you have given and the CNN that you have trained. You will get the image. And it will take a lot of time, because if the region proposals are higher, for example, in today's world, if you take a wide angle shot will have lots of scenarios, lots of information. So the number of region proposals will increase. So now let's try to summarize what we discussed right now for RCNN. That first means first purpose, potential region. Find out the potential regions that we use selective search for it, and we got the potential regions. Then we pass it through CNN, and then we get extract features through CNN, and then those features we have to classify using support vector machines, that is SVMs, and we try to pass it through a linear regression to find the bounding boxes. So means downcome, I would say, for this was the RCNN was very intuitive and very slow. Okay, so now let's talk about fast RCNN. That one thing that you might be noticing is that, why you need so many CNNs. I mean, if there are multiple region proposals that you have got, it's better to take out the feature of all images at once using one single CNN, and then based on the region proposals or region of interest, we can slice the features from those particular regions and then pass it forward. And you are very correct. So that is what fast RCNN did. That it performed feature extraction over the image before proposing regions at once, and then run the CNN over entire image instead of 2000 CNNs over 2000 overlapping regions. So from 2000 operations of feature extraction, you just came back to one. So that is what a lot of that brought a lot of speed up in fast RCNN. And since means deep learning was evolving, instead of using a SVM, you would either use a max layer or something better. Thus means you are extending the neural network, and you're not creating a single new model for doing the same task. Obviously training an SVM is pretty heavy task, and you don't want to waste time there. So that is what fast RCNN did. Now let's try to summarize through means this particular points. So region proposals are generated based on the latest feature maps. Okay, so first you do a convent, extract the features, and you anyway knew that these are going to by my region proposal. Using selective search, you will crop those particular features out of the big feature maps that we have generated. And instead of like training the SVM on all the different feature maps that we saw here, SVM. You don't need to do that. You will just train a single SVM. Instead of single SVM, you will use a linear and softmax layers to train a classifier, and then obviously a linear layer to regress the bounding boxes. So you reduced inform operations like number of CNN feature extraction you reduce, number of different SVM you reduce. So this gave us very considerable boost in speed. So again, but still there are bottlenecks. I mean, the selective cell search algorithm is still slow. I mean, you have to do segmentation, you have to do repeated segmentation to figure out, that which are my potential region of interest. To solve that problem, we bought something called region proposal network. That instead of doing mathematical calculation and again, do region create a neural network for it. uh, the researcher made a CNN, and using which they will take one forward pass and they will get all the proposals for the regions. Doesn't it sound like very convenient? And it is definitely very convenient, and that is why RPN was implemented. And from there, RPN kind of became a very big contributor to do the object detection in real time. So you were anyway using a CNN. So instead of moving across the image for finding the potential region, you will just move it and get image into lower dimension. You will extract the features, and you will get the region proposals. Okay, that these are the potential regions where my objects can be present using the output of RPN. And obviously RPN use anchor boxes, where and how anchor boxes looks is that instead of doing one sliding window at a time, it is a combination of multiple bonding boxes of different ratios, and it will slide them all at once. So instead of taking one bounding box at a time and slide it, you have, let's say, k number of bounding box, you slide all at once, and corresponding to each boxes you will get an output, that where a potential object of a particular ratio is present. And each anchor boxes gave you an objectness score for that particular region, and obviously four coordinates which is particularly representing a bounding box. Now this can be played with. I mean, the way RPN was defined was four coordinate box was getting output, but you can also have a polygon or a coordinate or anything for that sake to get an output. So, but still, I mean, the speed up which was bought by RPN, still you can feel that why again we are using the region proposal. Why not we can have one single CNN which can also extract the features, do the classification and give you the bounding box. They are also possible. We will discuss about that at the end of this if we have time. So but yeah, that is possible. I'm just giving a hint. So now let's summarize faster RCNN. That so we look at the feature maps, and you will have to select anchor boxes, that how many number of anchor boxes you need, and this decision is made on the basis of different kind of objects that is present in your image. For example, if you have a car and you have a person, then you will select anchor box like this for person, and you will select an anchor box like this for car, because it is having a wider aspect ratio. And person obviously would be sitting or standing, it would be more look like a rectangular box that is having more of length instead of that. And some other object, for example dog, cat, or let's say TV, you can use anchor box something like this which looks more of a square. Okay, so for each of these boxes, we output whether a potential object are present here or not, and we get around 2K scores and 4K coordinates out of the images, out of the features that we have extracted by using the anchor boxes. Although RPN is outputting you a bounding box coordinates, but it is still probable. It is not very much final that whatever the output that you are getting through the anchor boxes are good enough. So we still need a neural network that we call as neck or body, where faster RCNN is there, and it kind of tightens the bounding boxes there and makes doubly sure whether the object that we are trying to look belong to one of the particular classes or not. Okay, so let's get into more in depth of how this faster RCNN is working. So once we have, for example, if you look at this particular image, we pass it through a CNN, we get a feature map. Okay, this particular feature map we pass through a region proposal network, which will give me a potential region, and then I do a ROI polling. You might ask that why this is needed. See, different regions can be of different shapes, but you cannot deal with different kind of shapes if you are dealing with a computer, right? Because to me, I know that this is bigger bounding box, this is smaller bounding box, but how will computer know? So I will have to bring that bounding box in a particular format, in a particular size, so that it could be processed by computer further. So that is what we do through ROI pooling. And we also select our region of interest based on our the object that we are trying to look. So basically, if you summarize that, how faster means what is faster RCN? Faster RCN is RPN plus faster RCNN, and this is the new change that faster RCNN has brought by parallelly diverting the data to an RPN and then to a ROI pooling layer. Okay. So the core design of faster RCNN is as same as the original RCNN. The means the methodology, the idea remains same, that you find potential regions, extract features, and then see where object is present and what is the class of the object. So let's try to summarize this, that this means what is the change which was bought with the onset of different versions. So this RCNN, you can see that there's a selective search and external region proposals method. Region proposal obviously 2K, which has been a consistent across all the RCNN family. And here again, selective search plus external region proposal method is there. But instead of different CNNs, it has been replaced by one single CNN. And instead of different SVMs, it has been replaced by a softmax layer. And the number of processing has been significantly reduced. Now comes the faster RCNN. Here comes the region proposal networks, that is RPN. The concept of anchor boxes was introduced here, and instead of taking CNN and then taking each and every region proposal through selective search, it gives you regions in one shot. And then those features are again passed to classifier and box regressor, which first of all classifies that which object is present. And in the next, it will tell you that if a object is present, where it is present. So it will give you bounding boxes. The most let's discuss about bounding box formats as well. So the most popular bounding box formats that are used are either Pascal VOC, Coco, and nowadays one of the format that is becoming popular is Paddle. Paddle is basically parallel deep learning framework. There, a bounding box is represented using multiple formats. The value of the bounding box across Paddle or VOC or Coco remains same. It's just that their formats change. Okay. So yeah, means we talked a lot about faster RCNN, that they try to revolutionize something. So what I meant by that was this: the reduction in timing from 50 seconds in a standard hardware. If you are able to bring it to zero point 0.2 second, it means a lot for the industry. And this is what enabled a real-time object detection, which was earlier not possible. Let's say 2012, 2014, people were struggling a lot. And now speed up, it is around approx 250x speed up. And the good thing or the bad thing, I mean, the good thing is the speed increased. The bad thing is still the accuracy didn't improve much, because we talked about it, right? The philosophy of the methodology remains same, even in faster RCNN. But what you are looking here is coming from Pascal VOC dataset and testing. But now a lot of new kind of backbones have come, like SkewsNet or ResNext or different variation of ResNet, efficient det, and thus the accuracy have also shot up by a good margin. So this was about the theoretical thing about introduction to RCNN family and how it evolved over time. And the and why we are discussing about it, right? Means why, what does it mean? We are discussing this kind of things to enable this kind of industrial usage of AI, because earlier AI was huge. AI was popular, it was fashion, but people had to spend a lot of amount of money and computation power to enable it. But with the onset of this object detection real time, this kind of use cases, we are able to solve it, and it is benefiting the industry by huge reduction in the workload, as well it is helping the customers to get a better experience in any kind of the situation wherever they can be present. So yeah, so this is how the object detection is changing the world. So this was about object detection, and now let's take a code walkthrough. That okay, this all looks good, but how to implement it? How can we train a faster RCNN model? So today, by changing a little bit different, means about how the code is discussed, I have decided to, instead of going into the Jupyter notebook, let's take a deep dive into an industrial code itself, that how object detection is actually used in industry, right? Because because unless you apply it in some real world problem, you won't understand, or you won't get the feel that how deep learning is, what deep learning is, and how it is implemented. So if you see here, I have selected a very, very basic beginner friendly folder structure. That is the output, this is the source. SRC basically represents the code part, whichever is present here. Then there is a test folder and there is a train folder. Here basically you can input your data. Right now it is a data is not available here, so they are empty. But you can put down here your images and your annotation files. Now, the first file that we are going to discuss is config file. So config file is something, let us say somebody wants to use your code. It could be your manager, but they don't have a working knowledge about how a code is run, okay, and where to make change to get done certain things. So for that, reason we create something called configuration files. Here, to keep it very simple, we have created a config.py file, so that let us say you have to train a model, then you don't have to go and look in all the code pieces. You will just come to config.py, and you will adjust your batch size, image size, number of classes, the name of the classes, and obviously the output folder where you want to save the images. And let us say you want to save the outputs every epoch, and how frequent you want to save your model. That can also be configured from here, that save plots epoch and save model epoch. Now, the first and the most important step that is there in the deep learning is that define a data set and data loader object. Now you may ask that why I need a data set or a data loader object, because I can, load all the data at once in a numpy array, and then I can slice from 0 to 10, 10 to 20, 20 to 30, and then it should work, right? But that's not the case. Actually, every time we try to load all of the data, let's say you can have 10,000 or 1 lakh of data into your system, some kind of bottleneck gets triggered, and it cannot load images after a particular range because your RAM is limited, right? So that is why we always try to load the images into batches, so that we can do some perform some actions on there, and then we can take the decision accordingly. And this idea comes from stochastic way of performing operations, you can say. For example, a method you would already be aware of, like gradient descent, take one object at a time and then perform it on the whole population. But that will be also very slow, right? So it's better that you sample some batches from the entire population, expecting that sample should be enough representing the population. You try to perform some experimentation on there, you get some estimate, and then again you draw a sample out of the population, you perform some operations and try to estimate the parameter that you are trying to estimate. So this is where this dataset object helps us. So dataset object tells computer that where object is present and how to load the object, and also it will tell the computer that how many objects are present, so that the number of iterations can be defined on based on that. So there are like three major member to this particular dataset object is there. One is init, one is get item, then the other is len. Len is not defined here, it has been defined in some other way, but I'm just mentioning it for the sake of completeness. So there could be different kind of transforms that you want to perform an image. We talked about brightness enhancement, contrast enhancement, right? So they can be some of the transforms that images you want to increase the brightness by a certain extent before training them or before doing a prediction. Then there could be directory path. There is a height and width of the image with which you want to process the image, because selecting random size of images sometimes topples your model. It is a good practice to fix it also, but although it is not necessary. The number of classes that you want to define. So there is a member of the class, that is image path, which will get all the image path from the directory that you have mentioned, and obviously this list is containing all the images. Now get item, this init is telling you that where to find the data, and this get item will tell you how to grab the data. So for that it will try to see that how many images are present, and then if after it knows that how many images are present, it will try to load the image one by one, and it will try to do into obviously when you load the image it will come you as a uint8, that is the integer data type, but you want to convert it into floating type. Okay, then you would resize the image, and it is always a very good practice to convert your image in the range of 0 to 1, because dealing with data that is present in the range of 0 to 255 can bring a lot of issues for you. So we usually resize the image in 0 to 1 range and then try to perform all the operations. Usually we have selected here XML file format where data will be present. Basically XML is nothing but it could be JSON, it could be XML, it could be CSV, it could be text, it could be anything. Just for the sake of this particular experiment, and here I've selected an XML. So obviously the passing of XML is being done here, and now a image can have n number of objects, right? It could have 1, 2, 0, or 5 objects. So we go through a for loop and we try to find out the xmin, xmax, ymin, ymax. That is how we have defined the format of the object, like xmin, ymin, xmax, ymax. Okay, and then we convert them into boxes, and then we convert them into a format where by how our model is going to interpret it. And if you have to, let's say, perform some transformation in the image, like resizing, cropping, random cropping, box cut or something, you can do a self-drag transform which will transform the image into that particular thing. Okay, so length, this is finally the length is there, where it will give you in real time to data loader that what is the length of the data set object that you have taken. So here, let us say if my data was cat dog data set, just for the sake of completeness, I have chosen this. So I will create train data set, valid data set, and if you want, you can create the test data set as well. Just it's the matter of choice that I have not created here, but because when we do inference testing and model validation, we did do it there. So here, just two kind of data set is there: train and validation data set. So here, obviously, the argument, if we are looking the train directory resize, and the resize to basically x, and this is y, height and width, and classes and get transforms we have to pass to this dataset object. And there's something called data loader. Now the thing is that in data set object, you defined all the methodologies, that how many images are present, how to grab one by one image. But who is doing the heavy lifting of loading the images and then sending them to model? It is being done by data loader class, which is here we have selected the data loader of PyTorch because we are performing this hands-on session in PyTorch. So we define two kind of data loader objects, that is train loader and valid loader. And here different kind of arguments are possible, that you can mention number of workers, if you have to shuffle while grabbing the dataset objects, what is the batch size that you are trying to select. This all things are defined here. So this is just a main driver code, that if you just want to test this part of the code, how to run it. So it is a very good habit to always create a main section in bottom of every Python file you define, so that if anybody wants to test this particular piece of code, they should not have to run the whole code to see that how this particular piece is working. Now let's talk about the utilities. So this is an averager class which will take some array, and it will give you average of those particular arrays. And when we talk about arrays, they are going to be different kind of losses during our training, and depending upon the number of iterations, we will average it and give it back. And there's a function to reset. You will get to know that why this particular methodology of reset is there. There's a collate function. Collate function is nothing but it adjusts the data based on their different object size present there, and it tries to shape up the matrices in data loader. Then there are train transform and validation transforms. You can see that we are doing some transformation like flipping the image random rotate 90, which is always a very good practice. And also we have to convert the image at the end of the day to a tensor, because that is how the arrays are interpreted by these libraries. And this we have to two tensor we have to do both during training and validation. And we have created one more image which is like show transformed image, that it will give you a glimpse of how the data is looking like. Now let's come to the model. So here it's a very very beginner friendly, just taking the model which are defined in torch vision, faster RCNN. I could have chosen to define a faster RCNN model, but again it would not have made sense for a beginner friendly lecture. So we are directly picking up the faster RCNN model from the torch vision library. And if you have to do some perturbation here, obviously you'll have to define your own faster RCN. We are taking a pre-trained model because we don't have the time and memory to train a very robust model. So it's better to pick a pre-trained model. So this is how to do that. Okay, so now let's talk about engine, which is basically doing the training part. That here we have defined a train function. We have defined a train and iteration and loss as a global, because it will be used across iteration. Loss will be used across different iteration during training. So for making it visually more appealing, we have used a TQDM based progress bar, using which you will be able to know real time that which epoch where you are it is. Something will be there to see on the screen. And then we go through each and every iteration through this particular TQDM object. We take the list of the images, we take the targets. Now we pass it through a model. Okay, And this images and targets are obviously coming from data loader, which is being handled by TQDM as a iterator, because data loader is an iterator at the end of the day, right? So then for every iteration we calculate losses, and then we try to append it to a particular list, and then we do a backward propagation. Obviously these are very basic, so not I'm going into depth of it. That you take a back propagation and then you optimize your learning rate. So these two things perform that, and then obviously you increase the iteration by one. Now for every iteration we get a real-time description that what is the loss and what is the accuracy, that all you can configure. Right now we are just looking at the loss value because this is the most true indicator of how a loss is looking like. Then we have created a validate function as well. So what validation does is, instead of calculating loss, it would turn it down, and it will just take a forward pass, and from the ground truth it will see that what loss is there, but it won't calculate the gradients, because here we don't want to backpropagate the losses. So this is what the validate function is doing. And here everything we are performing now line by line. So here for this 80th line, you will see that we have created the model, we have ported it to the device where it is required. We have initialized our optimizer, which is stochastic gradient descent, because we are taking batches. Then we have initialized our train and validation loss and our iterations to one, obviously very obvious. Model name, it is depending upon you, your use case you can select. And then when we are going through number of epochs, we are doing the loss reset first. And obviously this, there are some good figures to give you a good analytics and graphics. Then we start the time, and for every epoch we check whether should we save model or not. So this if control statement is for that. And obviously means you can do plots the epoch as well, using the functions that you have seen in the utilities. So based on that you can take those decision here. And at the end uh, we have to obviously save the model, so that thing is invoked by using toss.save, where we are saving the model state dict in a particular path. And at the end we would want to close all the plots, and that is why this particular command is invoked. We have just added this. Sometimes the time that sleep is required, because sometimes the data is not offloaded from your GPU. So to make that possible, if at the end of every epoch or something, if you wait for some time, first of all you would get to look at very good plots, and also it will give some time to GPU to recover and offload and get ready for the next epoch. So that is what is that is why this time dot sleep is used. And at the end, when your model is saved, you can come to this inference code. And inference code, obviously you will have to load the model. You have to create the model, load the model, and you have to select the test directory. And this test directory is for that. Obviously we will load each and every image using batch size only one, because here we want to do it for prediction, because this is how real world works. Even in video feed you will get frames one by one, and for each and every frame you have to make prediction. Usually how it works, you can also make the prediction in batches, but yeah, usually, I mean, the way we start, I'm talking about it. So yeah, this is loading images, converting into a required RGB format, performing 0 to 1, converting into tensor, and then with toss.nograd, obviously because we don't want to calculate, we don't want to do backpropagation here, so we are setting it up. We get all the outputs, that what is the output of this particular thing, particular image, in terms of bounding boxes and classes, the way that we have discussed here, right? That you will get a bounding box and classes for each and every object, labels and bbox, a dictionary of list, I'm sorry, list of dictionary. So you will get the output, and at the end, obviously, a message will get printed that test predictions complete, and all the CV2 windows will get destroyed. So this is how a bare minimum industry level computer vision will work. And bare minimum, even a beginner person can implement a faster RCNN as an industry level code, which could be deployed as well. Obviously this is just the start. There are n number of optimization possible here. There are a lot of new workflows has come into picture, but if you are just starting up, I think this should give you a good heads up and a good start, and would definitely accelerate your work by some percentage for sure, so that you don't have to struggle a lot during the initial phase. So by this, in this code walkthrough, we covered about how to set configs, what it means by a data set and a data loader object. We saw that how you can easily define the model instead of doing trying to do a heavy lifting by defining the model from scratch. Just pull something from Torch Vision, just start experimenting with it. We also saw that that how a training pipeline looks like, how what are the steps of how a model is trained, and then we also went through the inference scripts using which we can deploy the model that we have trained into a real-time computer vision application. So this is it from my end. I am open for questions now. I'm open for discussions. So yeah, that's all.
Thanks a lot, Bijon, for that interesting set of, for the entire session, and um, you know, and for giving those examples along the process. Okay. There are a few questions that we have received. So the
Sure,
first
sure,
one
sure.
is like, what are some of the common ways to improve the accuracy of faster RCNNs? Can we use ensemble techniques for them?
Sure, 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 sure. Thanks for first of all, thanks for asking these questions. So when you are trying to improve the accuracy of faster RCNN, there is the first and the very beginner step that you should perform. You should check your annotations. There is where a lot of beginners make a mistake that they do not draw a tight bounding boxes. They leave a lot of gaps. So duly check that if your bounding boxes are drawn correctly, and while drawing bounding boxes, there are some set of rules that you have to follow. That if there is even a single instance of object is present in an image, it could be a case that there are a lot of instances are present and you just annotated 4 or 5 of them and left rest 3 or 4. Don't do that. You have to annotate each and every instance properly, and it should be a very tight bounding boxes. Now this is coming to the annotation. Now let's come to the data augmentation. Let us say you are missing or you are getting a lesser accuracy in test time. So for that, it means the data that is you are using for training is not reflecting the real world or the whole data set on which you want to run the test. So you can perform a lot of data augmentation there. I mean, color jitteration, cut mixes, image stitching, image mosaicing are some to name a few. If you perform this, then definitely you will straightforward get an improvement in the results. And apart from, let us say till now you have reached already 80 or 90% of accuracy, you want to scale the rest 10 or 20%. For this you have to play a lot with learning rate, and you have to play a lot with optimization, how to capture, how to extract all the information from your training data that is available. Now coming to the ensemble part, even after using this kind of methods you are not getting good results, then yeah, you have to create different models for different kind of objects to specifically identify them, and then you combine all the results to get final results, and that is what assembling is all about. But it is not recommended at the first go. Faster RCNN is good enough to tackle hundreds of classes at once if you have sufficient amount of data and you have performed good data augmentation. Yeah, that is my answer.
Okay, thanks. Another question is a more rudimentary one, but pretty
Hmm.
important. So, like,
Hmm.
so yeah. So, could you please clarify why did you prioritize loss value over accuracy as a metric? So, when you were explaining,
Okay.
yeah.
Okay, so see, there are some constraints. There are some constraint which you cannot miss. Now, loss value is one something like that. Now, talking about accuracy, accuracy is totally dependent on human being, right? It could be accuracy is like total number of right prediction upon total number of cases. It could be either precision or it could be recall. It could be sensitivity. It could be specificity, right? And it could be F1 score. Now, if you choose different accuracy, it should not be that you should get different model, right? Because at the end of the day you are looking at the same data, and using different accuracy metric you will get different result. But that should not mean that you have to change your model for each and every accuracy metric. So for that you have to use something very generic, which you can define for a particular data set, for a particular model. And there is where the loss comes into picture. Now, going into the losses, accuracy is a result of classification, right? And let us say if you use something called map score or something, it is a result of regression. How loss function is defined is it is a combination of classification loss and regression loss. So in a way it is a lot better metric than taking accuracy as a feedback and then improving model. You should better take loss as a feedback for a corresponding accuracy metric and then try to improve the model, so that your accuracy does not drive that how your model should be. Accuracy should be the byproduct of a good model, not you want to get a different accuracy, so you want to train a different model. It's not. It doesn't work like that. So that is my answer.
Okay, thanks for clarifying that. We'll take probably one last question. So,
Sure.
this is since you recommended to pick a pre-trained model, are there any tips that you can share for fine-tuning uh, the model for a new data set?
Okay. When we talk about pre-trained model, there are two possibilities for it. One is, pre-trained backbone, and one is pre-trained weights of a faster RCNN model or something like that. Okay. So backbone, you should not, try to mingle with it, because backbone is something which, I mean, you try to learn how to calculate low level features using backbones, that that what are the edges, what are the textures, and all those kind of things we want to learn. So that, making it learn over a smaller data set is very difficult, and usually that is why we pick a pre-trained model based on ImageNet or Coco or Pascal data set, because they has been trained, and it is a huge compute required to train those models. So for pre-trained model, pick a pre-trained backbone if it is possible, and if you want to customize it while picking the backbone, remove lots of layers. Is it 30 or 40% of layers, yeah, you have unfrozen in, and try to retrain it, but don't try to retrain it from scratch. It will consume a lot of time. Now coming to faster RCNN or something, you take a pre-trained model, let's say on Pascal data set, which if I'm not wrong, it is 20 or something like that, and you trying to do a prediction using that. Now that might not be recommended, because your use case will be very different. Your use case could be two class only. So there, don't use Pascal pre-trained model. I mean, try to train the faster RCNN from scratch itself using pre-trained equals to false. But to arrive at the right hyperparameter, you can use a pre-trained model, that what is the learning rate which is working, what is the alpha or beta value that is working out for you. For using to arrive at that, you can just use a pre-trained model and get an initial estimate, that what are the set of hyperparameters which can give you a better result quickly. Then unfreeze the whole model and try to train the whole model on your data set. And definitely, if your data set is pretty much well represented, and is actually a sample from a population, then definitely you should get some decent results, for sure. Yeah.
Okay. Well, with that, we are towards the end of the session. So,
Sure.
this is where I would thank you, Bijon, again, for taking the session, answering the questions that we got from community members. I'm pretty
Sure.
sure it
Sure.
was a insightful 1 hour for all those who attended it.
Sure. Sure. Sure.
And
Yeah.
thank you everyone for joining us live. We'll see you next Saturday. We'll be learning about XAI with TCAVs. So make sure to be there. We will see you very soon. And we're also starting off with boot camps. Interestingly, the pre-registration for AI Marketplace by AI Planet is also live. So you might want to check that out on aimarketplace.co. And we look forward to seeing you again soon. Take care. Ciao, ciao. Bye.
Yeah. Bye.